Alright, so the definition of the directional derivative of a function of two variables x and y at the point x naught, y naught in the direction of the planar vector u equals to AB is given by du of f of x naught, y naught equals to the limit of the following expression. The limit of, as h approaches 0, of f of x naught plus h times a y naught plus h times b minus f of x naught y naught divided by h, where of course here a corresponds to a in the direction vector u, and b here corresponds to the b in the direction vector u. And so this is the definition of the directional derivative, and the directional derivative measures the rate of change of the function f of xy at the point x naught, y naught in the direction of the vector u equals to AB. Alright? So my objective is to prove a theorem which I am going to introduce now. Alright, the theorem that I want to prove is the following theorem, and it says that if f is any differentiable function of the variables x, y, that then f has a directional derivative in the direction of any unit vector u equals to AB, and the directional derivative of the function f of xy in the direction u is given by the partial of f in respect to x times a plus the partial of f in respect to y times the value b, where b corresponds, of course, to the y-coordinate of the planar vector AB, right? And a here corresponds to the x-coordinate of the vector u. So I want to prove this theorem. Alright, so the proof goes as follows. I introduce the following function, which is a function of one variable, namely the function g of h, and it is a function of one variable. Now, bearing in mind bearing in mind that x naught and y naught happen to be constant values, so is the direction vector. So a and b here are constant values, so the only variable in this function is h, so this is a univariate function, in other words a function of one variable. So the derivative of this function, we know from the past, is equal to the limit at 0, as h approaches 0, of g of 0 plus h minus g of 0 over h. But this expression over here is actually nothing but this expression. Okay, this is actually what it is. It's this expression. So really so this is really over here, this actually is du of f of x naught, y naught. Alright, so this is actually du of f of x naught, alright, y naught, and of course is also equal to the derivative of the function g evaluated at 0. On the other hand, we can write that g of h is equal to f of xy, where x equals to x naught plus ha and y equals to y naught plus hb. Now, by the chain rule, by chain rule, we get that the partial of, or rather the derivative of g in respect to h, that g prime of h, is going to be equal to the partial of f in respect to x times the derivative of x in respect to h. The derivative of x in respect to h. So dx dh plus the partial of f in respect to y times the derivative of y in respect to h. But if you notice, this actually is equal to, this is actually just f sub x of the partial of f in respect to x, or the function f of xy, times a, the derivative of x in respect to h is just going to be equal to a, so I put here a, plus the partial of f in respect to y times the derivative of y in respect to h. The derivative of y here in respect to h is just going to be b. And now, putting h equals 0, okay, so if you put h equals 0 here, so putting h equals 0, so putting h equals 0, we get that x is equal to x naught and y is equal to y naught, right? So then we get that as a result of this, we get then that g prime of 0 is actually equal to f, the partial of f in respect to x evaluated at x naught y naught times a plus the partial of f in respect to y evaluated at x naught y naught times b. And of course, we know from one of the prior pages, that that the directional derivative of f evaluated at x naught y naught in the direction of u is of course nothing but, okay, g prime of 0. Okay, so this is what we get. So what follows then is that g prime of 0, then g prime of 0, okay, so g prime of 0 is equal to the directional derivative of the function f evaluated at x naught y naught, right? And that this is equal to, therefore, this is equal to du, okay, of f of x naught y naught, and equals to the partial of f in respect to x evaluated at x naught y naught times a plus the partial of f in respect to y evaluated at x naught y naught times b. And this is really what we wanted. Of course, let me add that x naught y naught is an arbitrary point where the function f of xy is differentiable. So we can actually conclude that this theorem says that the derivative of the function f of xy in the direction u is given by the partial of f in respect to x times a plus the partial of f in respect to y times b. And again, the point x naught y naught was a arbitrary point, so this is why we can assert this. Thank you for listening.